Hello, I am Ali Izzat Kasti. Today's lesson is about getting to know the RTD card and how to test and program it. We have used an LS Compact PLC model XEC-DR32H and added two expansion cards to it. The first card is the XBFDV0404A, which is an analog card with voltage output. And our second card is the XBF RTD 0404A, which is actually an RTD card and can be used for temperature measurement. We connected a PT100 sensor to this card, and from our analog voltage output, we connected it to the analog input of a G100 drive. As you can see in the image, a fan is also connected to our G100 inverter. For this experiment, we used 3 glasses of water, one glass with cold water, another with lukewarm water, and the third with hot water. The experiment is set up so that if the temperature is below 35 degrees, which is the case for the first glass you see now, its temperature is below 35 degrees. The frequency of our inverter will be set to 0 and our fan will turn off completely. If the temperature is between 35 and 45 degrees Celsius, the frequency of our inverter will be set to 30 Hz, just as you can see now in this demonstration, and our fan will start operating at a frequency of 30 Hz. If the temperature increases and goes above 45 degrees Celsius, then the frequency will operate at its maximum, meaning our frequency will go up to 60 Hz and the fan will work at its maximum power, which is 60 Hz. Now, if I put this PT100 sensor back into the first glass, where the temperature was around 35 degrees, you can see that the frequency is decreasing. Our frequency has dropped to 3 and our fan has turned off. Now let's get more familiar with the wiring and programming that we've done inside the PLC. Let's review the wiring together. As I explained earlier, we used 2 expansion cards. The XPIF-DV0S4A card, which is an analog voltage output card, and the XPIF-RDS4A card, which is an RTD card with 4 channels. This means that you can simultaneously connect up to 4 PT100 sensors to this card and have the temperature of each one separately available in the PLC. Here we've used just one sensor and connected it to channel 0. PT100 sensors are usually 3-wire. They have 2 common wires and 1 uncommon wire, which is usually a different color from the other 2. The wiring is done in such a way that the uncommon wire, the one with the different color, is connected to the A input of our RTD card, and the other 2 wires, one is connected to the B large input and the other to the B small input of channel 0. Also, from our analog output card, we take a wire from the positive terminal and connect it to the V1 input of our G100 drive. And from the negative terminal of our analog output card, we connect it to the CM terminal of our G100 drive. Next, we now connect this fan right here to the U, V, and W outputs, which are actually the outputs of the inverter. Since our fan here is in fact a single-phase fan, we just connect it to 2 of these outputs. One important point about this drive is that we've definitely set its FRQ to mode 2. Meaning it actually receives the frequency through the analog voltage input. The only setting that needs to be done on this drive is to set FRQ to 2. For the expansion cards, we definitely need a 24-volt DC voltage, meaning each of these cards separately requires a 24-volt DC supply to operate. The program we want to write in the PLC works as follows. When the temperature is between 35 and 45 degrees Celsius, our fan should turn on and the drive frequency should be set to 30 Hz. If the temperature is greater than or equal to 45 degrees, the fan should be on and run at 60 Hz. If the temperature is less than or equal to 35 degrees Celsius, the fan should turn off. Now, in the part where we said the temperature is between 35 and 45 degrees and the frequency should be 30 Hz, in programming we need scaling. As we explained in previous tutorials for analog output cards, here we're using the voltage output. We said that in the program we give it a value between 0 and 4000 and the output gives us a voltage between 0 and 10 volts. So if we want our frequency to be 30 Hz, we need to scale this and determine what value between 0 and 4000 corresponds to a frequency of 30 Hz. For this, we need to create a linear equation and find its formula so we can scale it here. As we explained before, we have 2 points, one at 0, 0, and one at 60, 4000. This relates to our frequency, which ranges from 0 to 60 Hz, and the 0 to 4000 is for the analog card. We need to provide this in the program. So, a line passes through these 2 points, and we need to find its equation. The slope comes out to 66, calculated using the formula. The line equation is y equals ax plus b. Here, b is the y-intercept, but since the line passes through the origin 0, 0, b is 0. So our line equation is y equals 66x. Now, if we want the frequency to be 30 Hz, let's see what value y becomes. In other words, what value between 0 and 4000 we need. Y equals 66 times 30 equals 1980, or approximately 2000. So if we input the value 2000 to the analog voltage card, the frequency will be set to about 30 Hz, which we'll use in our programming. Now let's enter the XG5000 software environment and write this program together. So let's enter the software environment now and proceed step by step. We switch to the XG5000. First, in the I/O parameter section, we need to define the cards we have. In this black bar at the top, we have to select the PLC model. Our PLC is the XEC-DR32H, so we select it here. In our first configuration, we need to define our first expansion card. Our first expansion card was the analog output card, which is XBFDDSF4A. And in the second configuration, I had connected the temperature cards. So in this section, we select the XBFR DSF4A card. Now there are a few settings we need to do here. In our first card, which is the analog output card, the channel, and in the second configuration, we had connected the temperature card. So in this section, we need to select the XBF RDSF4A card. Now there are a few settings we need to do here. In our first card, which is the analog output card, we enable channel 0. Its output range is between 0 and 10 volts. The input type on channel is also from 0 to 4000. For the second card, we do the same. We enable channel 0. Our sensor is a PT100 type. The temperature unit is in Celsius. We confirm this, click apply, check the all box here and confirm it. Now let's enter the XG5000 software environment for. First, as we explained in previous tutorials, we mentioned that analog voltage output cards need to be enabled. This step is necessary because these cards allow the system to generate the required analog voltage signals. If they are not enabled, the system cannot output the correct voltages, which may cause issues in operation. So from this section, I search for a move function here in the software. The move function is used to assign a value to a specific variable or output. In the input of this move, I set the value to 1. Setting the value to 1 activates the output channel, ensuring the analog voltage output card is enabled and ready for use. And in its output section, I need to select Auth Enable and set it right here in this section. So this now becomes channel 01 Auth Enable. We definitely need to make sure to do this step after the previous step. In addition, whichever channel we want to use, we also need to enable that specific channel. So I use another move function here, which allows us to enable the channel we have chosen. Again, I set its input to 1, and this time I select channel 0 output enable. Now, the analog output card should actually be enabled. So the next thing we need to do is to be able to read the temperature from that RTD card that's measuring the temperature for us. I'm going to use another MOV. If I search for MOV in the function section, well, since the RTD card was our second card, we need to look among these numbers with a 2. The ones that start with 2 are related to the registers of the card. So RTD becomes this 102 channel 0 temperature. I select this one, which is the relevant channel for temperature measurement, and name it with the abbreviation for temperature, temp, as a shorthand for temperature. This makes it easier to identify and reference later. I set its data type to integer, which means it will only store whole number values, and here is the temperature that the PTSD sensor now provides as its current reading. This value is updated in real time, reflecting the latest measurement from the sensor, so you can always see the most recent temperature data being reported by the system. Ben measures for us, we can view it here. Just one very important point to remember, the temperature we can see here actually has an extra 0 at the end, which means it represents the decimal place. For example, if our temperature is 35 degrees, it will display as 350 here. In other words, it shows the temperature with an extra 0, which is something we need to keep in mind as well. Alright, now we want to write a program together, step by step, making sure we understand each part as we go. To make our program look better and easier to read, we can use comments, which are notes in the code that help explain what different parts do. We also need to keep this in mind as we work. Alright, now we want to write a program together, carefully and thoughtfully. To make our program look better, more organized, and easier for others to understand, we can use comments throughout the code. We said that if our temperature is between certain values, then when we say 35 to 45 degrees, we mean that if the temperature is measured and found to be anywhere between 35 degrees and 45 degrees, our fan should turn on. The reason for this is to help prevent the equipment from overheating, which could cause problems or reduce its efficiency. At the same time, the inverter frequency should be set to operate at 30 Hz. Setting the inverter frequency to 30 Hz ensures that the fan runs at a speed that is effective for cooling, but also helps save energy by not running faster than necessary. So here, we actually have to set this up ourselves using the comparison function blocks. So let's go into the function section. First, we'll set up the first part together, meaning if the temperature becomes greater than 35 degrees. In previous lessons, we've explained that in the comparison functions, the comparison blocks was GT, which stands for greater than, so I use a GT block and enable it. We say that if our temperature, well, we've represented temperature with temperature. If the temperature is greater than 35, then here I need to enter the number 350. Keep in mind the point we mentioned before. We represent the temperature with an extra 0. It shows us quite clearly and unmistakably that we definitely need to account for that particular factor right here in this context. So if the temperature for any reason happens to go above 35 degrees Celsius, it gives us an output which we'll name output 1, and it's also in Boolean form, meaning it can only be true or false. This is the first part of the condition that we need to consider. The second part is that if the temperature at any point becomes less than 45, less than if, remember, it's the LT function, LT stands for less than. I'll enable this. So in the first input, I'll put temperature, and in the second input, I need to enter 450. I'll name its output O2, and its data type is also Boolean. Now for our condition to be met, it will only be satisfied when both of these are always... Alright, so for our condition to be met, it happens when both of these are simultaneously set to 1. So we need to AND these two together. If the A and D of these two is 1, then our condition is satisfied. Now we need to go back into the function section, and I'll select the function. I select the AND function here, which is used to ensure that multiple conditions must be met for an action to occur. After selecting it, I enable the function by clicking the appropriate option, making sure it is active. Then I set its first input to OUT1, which refers to the output labeled as number 1 in the system. I select the AND function here, enable the function, set its first input to OUT1, and set its second input to OUT2. Now from its output, I can connect the output using these lines, and then I go back into the functions again. I search for the move function. We see that if our A and D becomes 1, this move function is actually enabled. In the input section, it receives the value 2000, which is the same value we obtained together in the scaling section. I search for the move function. Well, we see that if our AND becomes 1, this move function is actually enabled. In the input section, they obtain the value 2000, which is the same value we got together in the scaling section, and we say that this value of 2000 should be stored in channel 0 of the data, meaning 01 actually refers to the channel. In fact, this 01 corresponds to the first expansion card, which was the analog output card. Channel 0 of the data, meaning 01, which is related to the channel. In fact, this 01 corresponds to the first expansion card, which was the analog output card. Its channel 0 is data. So we move the value 2000 into channel 0 of the data. This is so that our fan frequency is set to 30 Hz. The next part of our condition was that if our temperature becomes greater than or equal to 45 degrees, our fan should turn on and operate at its maximum frequency, which is 60 Hz. So here again, we use a function. We need to use it greater than or equal to, which is also known as GE, meaning greater than or equal. I will enable this now. For this part, we set one of them to temperature. We said if the temperature is greater than 45, which with the extra 0 we definitely need to include. So here we have to enter the value 450. So if the temperature which is being measured by the system is greater than or equal to 45 degrees Celsius, then the fan frequency should operate at its maximum possible value, which is 60 Hz. So here, once again, we use a function called move. And since I want it to work at its maximum capacity in this particular situation, the value that we assign here is 4. This ensures that the fan is running at full speed to provide the necessary cooling when the temperature reaches or exceeds that threshold. If we move the value 4000 here into our data channel 0 for the fan, then the fan can operate at a frequency of 60 Hz. And the last part of our condition was this. I load 1000. If we move the value 4000 here into our data channel 0, then with a frequency of 60 Hz, our fan can operate. And the last part of our condition was that if our temperature, if the temperature is less than or equal to 35 degrees, this means that our fan should turn off and the frequency should be set to 0, stopping the fan completely. In this scenario, we once again use a comparator function to check for the less than or equal to condition. To do this, we need to search for li, which is the abbreviation used for the less than or equal to comparator function in our programming environment. We enable this, set the temperature in its first input, and in the second input we need to set 35. We connect its output using these lines to the enable of another move command. And we move the value 0 into data channel 0. This is done so that the frequency is set to 0, which in turn causes our fan to stop operating. Setting the frequency to 0 is a standard way to ensure that the fan comes to a complete stop and remains off until a new value is entered. Thank you very much for your attention and for taking the time to follow this explanation.